Now only two more topics to go. One important, one not so important. One difficult, one pretty easy. I'm afraid the easier one is not so important one. What a surprise. Here we go. What is the distinction between mutually exclusive events and independent events? Well, here we go. This explains mutually exclusive events. Probability of A or B, or the probability of the union, is the sum of the probabilities. The reason? There's nothing to subtract. Normally you have to subtract away the intersection, which are counted twice, but there's nothing to subtract because A and B are mutually exclusive. In other words, there's no intersection. Intersection is empty. Intersection is empty. What do you mean by A and B are independent? That means the probability of A and B, in other words, the probability of the intersection, is the product of two probabilities. A good example of independent events comes from Earn model with replacement. And this problem actually continues from the previous problem. We did this one already, 2 red and 1 blue. 2 red and 1 green, okay, that's new. At least 2 red balls. They're just pretty much the same as the kind of problem we did in the previous video, so I'm going to leave this detail to the students. The answer key is here for all 3 problems with all appropriate color coding, so it's not going to be difficult to see. One more comment. Is it possible to have a mutually exclusive pair of events that are independent too? The answer is no. Mutually exclusive pair of events are never independent, and pair of events that are independent will never be mutually exclusive unless you cheat by some empty event or something like that. Why? Mutually exclusive means A intersection B is empty. But A and B are independent. That means, well, we're dealing with the intersection, and that is equal to probability of A times probability of B, which means one of the probability is 0, and we have impossible events there. That's cheating. That's what I meant as cheating. Of course, almost all pair of events will turn out to be neither mutually exclusive nor independent. Alright, that took care of section 4.6 of our textbook, and then let us spend the rest of this video on something really important and also difficult, Bayesian analysis. Well, mathematical description of Bayes' theorem goes kind of like this. When the sample space can be decomposed into 2 mutually exclusive events, B1 and B2, then conditional probability of B1 given A can be re-expressed as the right-hand side. If you have 3 mutually exclusive events that add up to total sample space, then more complicated. If you have more than 3, then even more complicated. And these mathematical notations are just too intimidating for 1000 level course, even though they are important. So what I'm going to do is to apply this Bayes theorem analysis, Bayesian analysis, into a tree diagram. And we're going to do that with the next example, which is very, very realistic. A laboratory blood test is 95% effective in detecting a certain disease when it is in fact present. However, the test also yields a false positive result for 1% of the healthy persons tested. Suppose that 0.5% of the population actually has this disease. Problem A. what is the probability that a person has this disease if the test result is positive? Problem B, what is the probability that a person has the disease if the test result is negative? Before going over to the solution of this problem, let us try to appreciate this setting of this problem. This laboratory blood test and this disease are of course fictional, and these numbers 95%, 1% and 0.5% of course will be bogus numbers. However, aside from those numbers, the setting is extremely realistic. I personally went through several laboratory tests kind of like these. Not long ago I had my liver tested through blood test, and some years back prostate too, and many others actually, and I have regular checkup. And most of the time those are all negative, but I have had some positive tests too. What do I do? Do I just go over to some painful therapy or something? No, what they usually do is go to second checkup, alternative checkup, which are of course a little bit more expensive, but further checkup is necessary in order to go ahead to the next step of treatment. Why and exactly how quantitatively, well, those kind of things will be answered with this problem. Now, before going over the solution, let's scrutinize these three numbers. 95%, which is obviously a probability, 1% another probability, 0.5% another probability. But there is a subtle difference between these three. The first one, 95% effective in testing a certain disease, is a conditional probability because of this phrase, when it is present. When the disease is in fact present, then this 95% applies. For a healthy person, it does not apply. So this is a conditional probability. Next, false positive for 1% of healthy persons tested. This time, we don't see the key phrase like when or if given that or something, but still you can see that this is a conditional probability because this applies only to healthy persons. Also, it says false positive. On the other hand, this 0.5% of the population, it says of the population, entire sample space. This is not a conditional probability. So there is a subtle distinction between these numbers, and you'll have to use the distinction to answer this question properly. Okay, let's begin with appropriate setup. Here is an initial attempt of the diagram. It is important that you take the first step right. The first step is not positive, negative, and have disease, no disease. The first step is have disease, no disease. And then the next step is positive, negative. Why? Because of this. 0.5% of the population actually has this disease. This is not a conditional probability. This is the original. The original must go to the first branch. So 0.5% of the population, right here where mouse is pointing, and by default, the other 99.5% have no disease. It'll have to go where my mouse is. And how about this 95%? That's for when the disease is present. So when have disease, 95% positive, and the other 5% will not be detected by this disease. For healthy people with no disease, 1% is tested positive, and then consequently the other 99% will be tested negative. As a matter of fact, interestingly, there are 3 probabilities given in this problem: 95%, 1%, 0.5%. But by considering complement probabilities, actually there are 6 probabilities to consider. And look at this diagram. There are 6 paths, 6 branches: 1, 2, 3, 4, 5, and 6. We are in a good setting. Let's put all those numbers in. Here we go. 0.005, that is 5%, have disease. That's what this is all about. And subtracting that from 1, we get the other complement probability, no disease. Let's go over to conditional probability. Those who have disease, 95% of the time the test detects it. The other 5% of the time the test failed to detect this disease, even though this person has a disease. The other situation for healthy person, 1% are false positive, healthy but tested positive. In other words, the other 99% of the time will be tested negative. Now this tree diagram is complete. Now, finally, let us answer these 2 questions. Let's answer this question. What is the probability that the person has a disease if the test result is positive? If the test result is positive, so that's the condition. And then that goes to denominator. Condition goes to denominator, right? And then the numerator will be intersection. In other words, this is a setting. Oh, by the way, let me go all the way over to, let's see, conditional probability formula here, and let's copy and paste it down here for a reference. Okay. The condition goes downstairs, intersection goes upstairs. Okay? All right? Like this. Condition goes downstairs, tested positive goes downstairs, and intersection goes upstairs. I did appropriate color coding as well here in this solution. Have disease and tested positive, red. No disease and tested positive, red. Adding those up, you're gonna get probability of being tested positive either way. And how did it get this and that? Of course, we followed the path. 0.05, this path, times 0.95. We get that. How do you get this? Have disease but negative, 0.05 times 0.05, we get this figure. All these numbers are coming from appropriate multiplication through the multiplication principle. Apply those into this conditional probability formula. We have the downstairs as the condition and the intersection as the numerator. Now, doing the computation using your handheld calculator is the easiest step. Do it and you're gonna get 0.03 something, 32.31% or something, 33.3%. In other words, given that the person is tested positive, what is the probability the person actually has the disease, the patient actually has the disease? Only 33.3% according to this blood test. Amazing, because it says 95% effective. But this is a reality. In other words, should you start some painful therapy like chemotherapy with 32%? Of course not. You need second opinion, you need second testing, and so on and so forth. Now, what about the other probability? Condition is now negative. If the test result is negative, in that case, the blue, this one, and that one will go to denominator, and the numerator will be disease and negative, this one. Do the computation, you're gonna get, oh, really small figure. In other words, if the test comes out negative, the probability that the person has the disease is really small. What are you gonna do if you're a doctor or a medical personnel? Well, if the test comes out negative, don't have to worry about it, good news, and then let's dismiss the patient. If it comes out positive, do not start treatment right away, do further testing. this kind of problem is very, very realistic.